In this video, we're going to show an outline of the proof of the backpropagation algorithm, and specifically the update regarding the backpropagation in neural networks. So the way we perform backpropagation in neural networks is that we will have an error, and we would like to backpropagate the error from the output layer all the way to the input layer. And based on this propagation, based on this change in error, we would like to change and update the weights for the different hidden layers of the neural network. So let's assume this general case in which we have this L hidden layer that is connected with the L-1 hidden layer with weights W with an exponent here denoted as L. And the L hidden layer is also connected with the L+1 layer, which is the next layer, with a set of weights that are being denoted with an exponent L+1. So the way in order to perform backpropagation, we use essentially the update from the gradient descent in order to update each of these weights of the neural network proportional to the change of the error rate or the change of the loss function with respect to that specific weight. So J is the loss function, the cost function of our neural network, and the derivative of our cost function for each of the weights W from the inner layer L Kj means that weight is the weight that connects the jth node of the L-1 layer with the k node of the lth layer. So that change of loss function with respect to this weight is proportional to the result of the activation at the L-1 layer multiplied by the error that comes here, that is being propagated here at the kth node of the L layer. Now this error, which is being denoted as delta KL, can be written as that update rule here. So what this means is that the error that reaches the K node of the L inner layer is now proportional to the first order derivative of the activation function at that node. So essentially the first order derivative of this activation function multiplied by the sum of the errors that are being propagated for the nodes from the nodes of the L+1 layer. These errors are denoted as delta with an exponent L+1 and are all being multiplied by the corresponding weights that connect the kth node of the L inner layer with all the nodes of the L+1 inner layer. And this is what essentially this sum is all about. So what we want to do is here we would like to apply the chain rule in order to reach an expression that starts from the first order derivative with respect to this weight Wkj that connects the L-1 layer with the L layer. And we iteratively apply the chain rule in order to connect this first order derivative with respect to the first order derivatives that correspond to these errors. We also note that by definition, the error that delta M of L+1, meaning the error that starts from the mth node of the L+1 layer, so this error here, is equal to the first order derivative of the cost function with respect to the input of that specific node. And if you think about it, this error says how much our cost function changes if the input in that specific node changes. So what we're going to do in this proof, we are going to start by expressing this first order derivative here, first with respect to this variable, then with respect to this variable, and then with respect to these delta variables. And the reason is because we want at the end to have essentially this expression here. Before we do that, let's start just by some expressions that result from the forward propagation of the neural network between layer L-1 and layer L+1. So essentially the input of the L inner layer at the K node is equal, just from the process of forward propagation, to the inner product between each of the inputs at this node, which are all the nodes of the L-1 layer, multiplied by the corresponding weights WK of L. And this is what this expression here says. So this input here of the K node at the L inner layer is equal to the sum over all these nodes J of the L-1 layer of the weights that connect the hidden layer L-1 with the hidden layer L, multiplied by each of these activations, each of these outputs of the nodes at the L-1 layer. Now the activation alpha KL, which means the activation again of the kth node at the L hidden layer, is equal to the activation function f of the input of that node. That's pretty straightforward. Finally, if we want now to perform one more forward propagation in order to find the input of the M node now at the L+1 hidden layer, we are going to see that this input again is the inner product between all the weights that connect the L with the L+1 hidden layers, multiplied by each of the outputs of the L hidden layer. So essentially it's the sum that runs over K of the weights. Now these are the weights that connect L with L+1 hidden layers, times the outputs, the activations that result from the L hidden layer. So now let's start by iteratively applying the chain rule for solving this first order derivative. So again, the first order derivative of the cost function J with respect to error WKJ of L, the weight WKJ of L. Again, as a reminder, this is the weight that connects the J node of the L-1 layer with the K node of the L layer. We iteratively apply chain rule, and then we express this first order derivative with respect to this variable zeta z of KL. So just a simple application of the chain rule. This will be the first order derivative of J with respect to the variable z times the first order derivative of variable z with respect to the weight WKL. Now, this expression here, this first order derivative here, is actually known because the input of the K node of the L layer depends on this weight and is actually the activation function of the previous layer. So essentially is the activation function A of the layer L-1 from node J. And the reason for this is that we can actually compute that from this expression. So we can see here that if we take the first order derivative of Z of K with respect to WKJ, then the only thing that remains from this sum is essentially this activation here, which is what we substitute for this first order derivative. Now, since we have the first order derivative of the cost error with respect to Z, we apply one more chain rule to find the first order derivative of this cost error with respect to the activation function alpha. And this first order derivative will be again the cost error of j with respect to alpha multiplied by the first order derivative of alpha with respect to the initial variable z. And here we have just performed the substitution of this first order derivative here from the previous calculations. Now here we have another non-first order derivative, the first order derivative of alpha with respect to z. So we have already said that alpha of k is equal to the activation function of z. So basically alpha of k is here, z is here, and the thing that connects those two is the activation function. Therefore, the first order derivative of alpha with respect to z is going to be the first order derivative of this activation function with respect to z. Therefore, this thing can be substituted with f prime here. So now we have an expression of our cost with respect to that variable alpha, meaning the output of the L layer. What we want to do is expand this one more time. So we want to actually now go ahead and reach the L+1 layer. And the way to do that is now to perform another chain rule by expressing this cost with respect to each of the inputs of the L+1 layer. And the reason that we do that is now because this basically affects all of these inputs of the L+1 layer. So by performing one more chain rule, now we have to consider all the inputs. Therefore, we get the sum of the cost function with respect to zeta. These are our zetas. These are all our inputs over basically all the nodes of the L+1 hidden layer. Again, for each update, for each of these terms of this sum, we have the first order derivative of j with respect to z of m multiplied by the first order derivative of z of m with respect to the first order derivative of alpha, which was our initial variable. Having said that, now we can see that by definition, the first order derivative of j with respect to the input zm at the L+1 hidden layer, by definition, this thing is the error that is being propagated at the L+1 hidden layer. Therefore, this first order derivative here can be substituted by this error here. Now, the first order derivative of z of m with respect to alpha is equal to the weight that connects these two. So the first order derivative of z of m with respect to alpha is now just equal to this weight. And this is very similar to that calculation that we saw in the previous a few steps before. Therefore, this here can be substituted by the weight that connects nodes m and k of the layers L+1 and L respectively. And basically this is it. So we managed to show what we wanted to show in the beginning, which means that the first order derivative of the cost error with respect to some weight, wkj, basically this weight here, is equal to the output of the L-1 layer at node j multiplied by the error that is being propagated from the previous node L from the previous layer L at node j. This error here, we show that it is equal to the first order derivative of the output of the Lth node multiplied by all the weights that come, by all the errors multiplied by the corresponding weights that come at this specific node. In the next video, we're going to provide an example of how this update rule would work for a simple neural network.